Hi all, this is Alan with Bothell STEM Coach, and today we're going to be looking at the AP Physics C 2019 Electricity and Magnetism free response questions, and this is set 2. So if you're looking for the set 1 free response questions, check out my channel and look for those other videos. So this is the set 2. This is the first year they kind of split them up for some reason. I'm not entirely sure. I don't have any relationship with the College Board. So okay, so and as usual, if I have any corrections to make, I'll put them in the description below. I attempt to try to do them right the first time as best as possible, but sometimes I do make mistakes. And I also have links to the PDF solutions that I'll update and make sure they're correct as you guys point out any mistakes that I might have made. So let's take a look. The circuit represented above is composed of 3 resistors, and resistance is shown, a battery of voltage V0, a capacitor capacitance C, and a switch S. The switch is closed, and after a long time, the circuit reaches steady state conditions. So let's kind of, I'm going to redraw it with a closed case, and it's steady state. Answer the following questions in terms of V0, R, C, and fundamental constants as appropriate. Derive an expression for the steady state current supplied by the battery. Well, in steady state, the capacitor is fully charged and it's opened, or you think of it as open, so no current's going to flow. So this is sort of disconnected. So for A, the current is just these two voltage divided by these 2 resistors in series. V0 over 3R. Okay. Derive an expression for the charge on the capacitor. Well, let me erase my things here. So when it's connected, this voltage has to match this voltage, because if there's no current flowing through here, the voltage here across this capacitor is the same as the voltage. Like, this is no voltage, so it's the same as this voltage here. And so how do we know what this voltage here is? Well, this voltage is simply the current times this resistor, right? Because the voltage drop across here would be just the I that we calculated times R. So the voltage then is V0 over 3R times R. So this is IR, and it's V0 over 3. Okay, that's the voltage across the capacitor. Derive an expression for the energy stored in the capacitor. Energy, 1/2 CV squared. 1/2 C times V0 over 3 squared. And that's 1/18 C V0 squared. Okay, these should all be right. CV squared. I don't know what the heck I did in my solutions. RC, yeah, 1/2 CV squared. I don't know what I think, yeah, never mind. My solutions are messed up here. I don't know why I wrote the equation right, but then I just did something weird here. Okay, now the switch is open at times t equals 0. So now we're going to open this up. And write but do not solve a differential equation that could be used to solve for the charge Q of t on the capacitor as a function of time after switch is opened. Okay, so once it's opened, right, this thing has an initial, well, you just need to solve the differential equation. What's going to happen is the voltage across the capacitor is going to decrease, right? Because initially at time 0, the voltage at the capacitor is V0 over 3, and the current is going to flow. And what's the basic equation for a capacitor is the current is equal to C dV dt, right? So, but the current is also equal to the voltage divided by these 3 ohm. Like these current is going to be three resistors in series. So let's make sure we get the polarity right. This is the V, and then when you do the I, it's technically the I in this direction. Yeah, so that would be negative VC over 3R is equal to C dVC dt. Okay. Now, you could just simply, this would be a differential equation you could solve. You could solve for V, and then you could solve for I, and solve for Q. I don't know if they want you to do anything else. I is equal to dQ dt. So that might be like something to consider in terms of the differential equation. I didn't really consider, because normally I just solve for the voltage, and then once I have the voltage, I can calculate the charge by integrating it. But or actually, sorry, no, then I would do Q is equal to CV. Yeah, right, and that would be the charge on the capacitor. So that's, I think that's okay. I don't know if you would set up a differential equation in terms of Q. I guess you could replace VC with Q over C, right? So I could do negative Q over C 3R is equal to C dQ. Well, dVC dt would be dQ dt, all of that divided by C also. So those C's would cancel. It's sort of a linear proportionality. Yeah, so I would just get negative Q over 3R is equal to C dQ dt. So I assume you would get credit, like if you did this and then indicated you would just take your answer to VC and divide by C. I think that would be okay. I mean, that's my opinion, at least. That would be okay. But I don't, I'm not close for. So either, but as long as the differential equation generally looks about like that. So calculate the current resistor R immediately after the switch is opened. So immediately when the switch is opened, we have a voltage V naught, and like we said, it's going through 3R. So it's going to go V. So I is going to be the V naught over 3 divided by the total resistance of the two in series. So that would be 1/9 V naught over R. Okay. On the axis below, sketch the current in the circuit as a function of time from t equals 0 to a long time after the switch is open. Explicitly label the maxima with numerical values or algebraic expressions as appropriate. Okay. So it's gonna start with this current is gonna decay to 0. Oops. I don't know if you guys do RC time constants, but I don't think you need to plot that. And this would be 1/9 V naught over R. So the current is just gonna decay to 0 over time because the voltage is gonna drop and then the current will drop, and it's an exponential decay. Is the total amount of energy dissipated in the resistors after the switch opened greater than, less than, or equal to the amount of energy stored in the capacitor calculated? Dissipated in the resistor after the switch is opened greater than, less than. Should be equal to conservation of energy. All the energy lost in the capacitor has to go somewhere, and it went out through energy lost through the resistance. So let me just double check. Yep. All right. So let me know how you did, and in the comments below, and also note if you have any questions or if you noticed anything I did you thought that I did wrong. I'll see you in the next video.